Right, great. I'll move on to the second problem. Yeah, yeah, yeah. I might be a bit biased, but I think the second problem was the hardest in my opinion, even though like the solution ends up being really short, but let's go over the problem. Yeah, so uh, so there's n cows, um, and each one has some kind of, yeah, uh, wait, yeah, um, yeah, so each one has an ID. Oh yeah, sorry, this is not problem three, this is problem two. Okay, yeah. Um, okay, yeah. Um, yeah, so there's n ID numbers. And then for each unique ID, there's ni cows who share it, right? Yeah. So basically you get like some kind of graph, right? Uh, Interesting. I didn't see this. Okay. Yeah. So you have like some kind of graph, right? Uh, yeah. And then uh, yeah. So like basically there's groups with a bunch of no values, and these are like numbered. So this is like, let's say this is numbered x, and then this numbered a minus x. And then also this is numbered b minus x. Uh, yeah. So basically like for any two things that sum up to A or any two things that sum up to B, they can communicate with each other, right? So there's like an edge between all of these pairs. And then there's also an edge between all of these pairs, right? Yeah. So that's like some kind of, yeah, these are the connections that you're given in the problem. Yeah. And then the problem is asking you to find the maximum matching. So basically, you want to find the maximum number of connections so that like no two are touching each other, right? Yeah, yeah. So this is a sample case. Yeah. So yeah, yeah, yeah. So you want to maximize the total number of connections that can be made. Yeah, yeah. So let's consider like uh, as a warm-up, the first case, right? A is equal to B, right? So here the connections are only made between like X and A minus X, right? So there's like some kind of structure here, right? So A over 2 is in the middle, and then you have like all these locations uh, where the cows have these IDs, right? And basically there's a bunch of connections. All the connections are going to be nested in some sense, right? It's going to have this nested structure. Um, yeah, right. Yeah. So then actually solving this is, yeah. So you can just consider all these things independently and solve for each independently, right? Right. So if there's like Y cows here, and then there's Z cows here, then you just match the minimum. So this contributes min YZ to answer, right? Yeah, so that's how you do this thing where A is equal to B, right? Yeah, so it's where it's two subtasks. Yeah, so let's consider like the more general case. We can assume without loss of generality that A is strictly less than B, right? Yeah, so we're doing this problem like at least when I was doing this problem, I tried thinking of DP. I don't think there's like any, maybe there is, but I couldn't think of a straightforward DP. So maybe there's something greedy that suggests maybe there's something greedy that you can do for this problem. Yeah. So yeah. So you can try considering like the optimal solution, right? Yeah, so you can try considering the optimal solution. Yeah, and then you go from left to right. So just like try considering like simulating the optimal solution, right? Uh, right. So you have a lot of segments, right? So the segments are either connected between like x and a minus x, and you also have other segments that are connected between like some x and some b minus x, right? Yeah, so basically you're given all these segments of all these connections, right? Yeah, and I'm just gonna define like AI to be like, because we're gonna match cows and kind of like remove them. So we can just define this to be like the number of cows remaining at I, location I, right? Yeah, so you have like all these segments where there's connections, right? So let's consider simulating the optimal solution and going from left to right. And when you're simulating, uh, basically, yeah, uh, you're iterating over the left endpoint from left to right, and then you're matching it with things to its right, right? So yeah, so I'm sweeping over some value x, um, and then I'm basically iterating, uh, yeah, sweeping from left to right, iterating over left endpoints, right? So let's say I currently x is over here, right? So in the beginning, uh, yeah, so x can have up to two things that go to the right. One of them is going to be a minus x. Let's say a is over here. And then the other one's going to be b minus, sorry, I meant a over 2 is the dashed line. So this dashed line is a over 2. Yeah, this is a minus x. I'll write this again to the side a bit more cleanly because it's cluttered with all these things. Yeah, so a minus x is here, let's say, and then let's say b minus x is here, and b over 2 is here, right? Because this is basically like we're reflecting over b over 2. B over 2 is the average of these points. Yeah, I'll write this again. So we're simulating the optimal solution where we're iterating over left endpoints. We're just trying to like learn what the optimal solution looks like, right? So I'll write this again. I'm writing this again right now, a bit more clearly. So x over here, and then a minus x over here. Yeah, and then yeah, you have x over here, and then b minus x over here. Right? And then yeah, so we have a over 2 is the midpoint of this, and then b over 2 is the midpoint of this, right? Yeah, and then we can also take note that um, if there's also a connection that involves a for b minus x, then you're gonna reflect across a minus a over 2. So it's gonna be way out here to the left, right? So this is like a minus b minus x, right? Yeah, so I guess some intuition for what kind of thing we want to do here is um, we're simulating the optimal solution where we iterate over left endpoints. So this is the last time we're ever gonna touch b minus x, right? B minus x has at most two neighbors. Either you reflect across b, which is here, or you reflect across a here. And we already dealt with this segment, this left endpoint, way back. So we're not this is the last time we're going to encounter b minus x, right? So if there's ever any cows remaining at b minus x, then we want to like then we want to match uh like cows from x with cows from b minus x, x with b minus x. Yeah, so this motivates like some kind of algorithm, right? So the algorithm, yeah, yeah. So an algorithm It's like iterate over left endpoints. And since we're never going to touch b minus x again in the future, first try, first match x's with b minus x's. And then when you no longer can do that, when you after you keep matching by like subtracting the min of number of cows here and number of cows here, then you should match x's with a minus x's. Right? Yeah, so this idea of like trying to consider the optimal solution and then simulating it from left to right motivates this kind of algorithm. Yeah, and you can try coding it. It ends up getting accepted. So that's like a proof by AC. But we can try to like think about how to prove this, right? Yeah, but this is this is like the solution. Yeah, so if you coded it, yeah, this thing gets AC. But yeah, like yeah, it's actually like kind of the reason I said this may be like the hardest problem in my opinion is I think like proving this is actually yeah, it's not it's like a kind of yeah, it's like a bit hard to like reason about. But yeah. Yeah, so like the reason why you want to prefer things at b minus x is like if let's say there's already things that are paired to a minus x, and then there's things that are paired to b minus x, right? And if you're allowed to pair more things to b minus x, you can move things away from here and then transfer them to here. And it's not gonna hurt your solution, right? So if there's ever like more leeway to connect things between x and b minus x, and there's things that are already connected to a minus x, it doesn't hurt to transfer them so that x is connected to b minus x, right? So this tells us that we want to prioritize b minus x, right? And now the question is, why do we want to match x's with a minus x's, right? So some like an idea is like, let's say x is over here, a minus x is here, and then this is like the neighbor, this is like b minus a minus x, right? Right. So let's say we have like space to transfer more things to here. It doesn't hurt to transfer things from here to here, right? Yeah, yeah. So there's like some intuition about why this works. But yeah, any questions? Yeah, so if there's no questions, we'll move on to the third problem. Yeah, so there will also be a time for questions there at the end. Yeah, so let's look at the third problem.